Hey everyone, welcome to The Explainer. Today, we're decoding a quiet but absolute revolution that is happening right under our noses. You know, the physical objects all around you, whether it's the car parked in your driveway, a jet engine soaring overhead, or even the microscopic materials inside your smartphone. They are all secretly being engineered, tested, and perfected inside a boundless digital universe long before they ever exist in the real world. We're talking about the computational simulation revolution, and honestly, the sheer scale of what's happening right now is just going to blow your mind. Okay, let's just dive right into it. Here's our roadmap for today. We'll start off with the simulation revolution. Look at how we're supercharging engineering workflows, then enter the world of exascale and AI, before zooming all the way down to designing materials from scratch, and we'll wrap things up at the quantum frontier. All right, part 1, the simulation revolution, or the multi-billion-dollar digital world. To really grasp the micro details later, we first need to zoom out and look at the macro level. Basically, computational modeling is allowing massive industries to analyze, predict, and completely optimize real-world systems entirely in software. We are effectively killing the need for slow, incredibly expensive physical prototypes. To put the scale of this into perspective, the global simulation software market sat at about $12.14 billion in 2023. But get a load of this projection. It's expected to rocket to over $34 billion by 2032. This massive growth is mostly being driven by the manufacturing and automotive sectors. And why? Because these guys are desperately trying to mitigate risks, speed up their innovation cycles, and of course, slash costs. The visual proof of why this matters is just incredible. We're looking at advanced computational fluid dynamics here, mapping the exact, incredibly chaotic, turbulent airflow over an elemental RP1 track car. In the past, you'd have to physically build the car, stick it in a multi-million-dollar wind tunnel, and just hope your sensors caught the right data. But now, engineers can map this chaotic flow in brilliant, granular detail entirely digitally. They can twist and tweak the virtual geometry in real time to slice through the air with absolute perfection. And nowhere is this more of a game changer than in Formula One. Take a look at the intricate aerodynamics on this F1 front wing. In F1, a tiny 0.3% difference in performance is literally what separates first place from third place. Now, historically, teams would have to manufacture physical prototypes for like 90% of their ideas just to see if they worked. Today, it's the exact reverse. They test their virtual parts in incredibly high-fidelity simulators, and they only physically manufacture the components that have already proven digitally that they can deliver that critical 0.3% edge. Moving on to part 2, supercharging engineering workflows and crushing the time barrier. So as these simulations got more and more detailed, they hit a massive wall, mostly involving time and computing power. 1,000. We've all felt the pure agony of staring at a computer loading bar, right? Well, imagine waiting 1,000 hours. That actually used to be the standard wait time for complex, implicit, finite element simulations in structural engineering. That is nearly 6 weeks of just waiting around for a single digital result to compute. It was a massive bottleneck for innovation. But the breakthrough here is staggering. For structural engineering runtimes, we've gone from that 1,000-hour wait down to literally just a few hours. How do we do it? Through these incredible collaborations between software vendors and hardware giants. A perfect real-world example of this is Rolls-Royce. By optimizing their software, specifically using the Ansys LS-DYNA implicit solver so it could run on modern parallel exascale architectures, Rolls-Royce completely collapsed their structural engineering workflows. What used to be a 6-week wait is now entirely done before they even head to lunch. All right, part 3, enter exascale and AI, our new silicon reality. This brings us to the real heroes of this paradigm shift. We're moving away from traditional single-precision scaling, and we're shifting the center of gravity toward workflow-defined architectures powered by AI and exascale supercomputers. But the crazy thing is, we're still just at the very beginning. Currently, only about 23% of manufacturing companies are actually using AI in product development. That means 77% are still sitting on the sidelines. But consider this. Generative AI is projected to boost product research revenue by an astonishing $328 billion. So you better believe that 23% adoption rate is about to absolutely explode as companies race to integrate AI into their simulations. To handle all these heavy AI workflows, you need unbelievable hardware. Enter systems like the Kestrel supercomputer over at the National Laboratory of the Rockies. It operates at 56 peak petaflops and powers over 500 different energy modeling projects. These machines are so powerful and they generate so much heat that they require massive liquid cooling infrastructures just to keep from melting down. But it is so worth it because Kestrel is currently running AI workflows to do things like screen for critical mineral-free electrocatalysts and simulate really complex gas-liquid flows to optimize industrial bioreactors.
Which leads us to Section 4, designing materials from scratch, down at the atomic microscale.
I want you to take a breath and just slow down with me for a second here. We are leaving the macro world of massive jet engines and sprawling data centers and entering the truly awe-inspiring realm of the atomic microscale. The key player here is MLIPs, or machine learning interatomic potentials. For decades, computational chemists were stuck. They had to choose between highly accurate quantum models that took forever to run or fast models that were wildly inaccurate. Well, MLIPs change everything. Pre-trained universal potentials like Atlantis' PFP now deliver quantum-level accuracy, but at the blistering speed of those classical models. This finally enables true atoms-to-engines workflows. We can literally design and stress-test brand-new materials virtually, atom by atom.
And all of this builds into what's called the modern materials tetrahedron. We're no longer just looking at matter in isolation. We are combining it with vast oceans of data, sophisticated AI models, and autonomous agents. Researchers are finally ditching the old method of brute force screening materials at absolute zero. Instead, they're using these tools to predict real-world, finite temperature stability. They can actually see how a brand new alloy is going to degrade or exactly how hydrogen will diffuse through it under real-world extreme conditions.
And finally, Section 5, the quantum frontier, where we start predicting the unpredictable.
We have officially reached the bleeding edge horizon. Because as insanely powerful as classical AI and exascale computers are, they do have physical limits, especially when it comes to power. And this is exactly where quantum computers enter the chat. The relentless pursuit of larger and larger AI models has created a very real energy crisis. Just look at this staggering comparison. Training just one large AI model can consume around 10 gigawatt-hours of energy. To put that into perspective, that is roughly the entire output of a nuclear power plant running at full capacity for 10 straight hours. We simply can't sustain this. But quantum processors, which manipulate vast mathematical vectors simultaneously, might be the key to curbing this massive energy spike, letting us do exponentially more work with a tiny fraction of the power footprint.
And we are already seeing the incredible results of combining these two worlds. A recent study demonstrated a quantum-informed AI workflow, and it's super cool. They used a 20-qubit quantum computer as a preprocessor. Step 1. The quantum machine uses entanglement for feature extraction. Step 2. It isolates invariant statistical patterns hidden in the chaos. And Step 3. It feeds those pure, refined patterns into a classical AI for training. The result? This hybrid approach achieved 20% greater accuracy in predicting the absolute chaos of complex fluid dynamics. It completely outperformed models that relied on classical computers alone.
Which brings us to the ultimate question. We've gone from wind tunnels to exascale digital twins. We've gone from agonizing 1,000-hour waits to Rolls-Royce crushing workflows before lunch, and even designing new materials atom by atom in seconds. So when AI and quantum computing fully merge, and our predictive models are totally unconstrained by energy and classical computing boundaries, what physical limits are actually left to break? I'll leave you to think about that one. Thanks so much for joining me on this explainer, and stay curious.